Okay, in this video I'm going to do problem number 6 from homework number 5, and hopefully this helps studying for the exam. What I'm going to do is I'm going to go ahead and do it right here on the homework page, and we're given two bit sequences, and so what I'll do is I'll copy them into the spots 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0 is the first one, and the second one is 111, 0, 100, 11, 0001, so to speak. Okay, so we're asked to do all these different types of encoding, and what I'm going to do is just get out the slide and say NRZ-L, non-return to 0 level, has a 0 bit giving a high voltage, a 1 bit giving a 0 voltage. Sort of upside down what you might think is the easiest, most straightforward way of encoding. And so the NRZ, this is going to be the NRZ signal, is going to give high voltage value for a 0 and a 0 voltage value for a 1. Very simply, high, high, low, high again, 3 lows in a row, a high, a low, and a high. Okay, and I think I'm going to go ahead and do both of them while I'm at it. Once I get used to doing a certain encoding, sort of helps to just do that one. So I get a high on the zeros and a low on the ones. That's about as easy as it gets. Okay, so those are what those signals look like there. For the NRZ-I, a 0, okay, so it's an inverted, and basically the 0 and the 1 tell whether or not there's a transition rather than what the actual voltage is. So 0 is no transition and a 1 is a transition. And I guess you have to decide, whether you're going to start at a 0 voltage or not before the first bit on this one, or else so you have to just make a decision. Let's assume that we're coming in with a 0 voltage on the previous bit, and so a 0 gives no transition and a 1 gives a transition. So no transition, and when we hit a 1 we get a transition. Here we hit another 1 and get another transition. Here we have 2 zeros, so no transition. Here we have a 1 transition, and then a 0, no transition, so we're going to stay up high. And then we hit 3 1s in a row, so we're going to transition, transition, transition again. And now we have a 0, we stay at low, transition up to high, and then we stay up at high here. Okay? For the other one, again, we'll assume that we start with a 0 voltage here, and we get 3 1s in a row, so 3 transitions in a row. 1, up to high, down to low, transition to high, 1, 2, 3, and now we have a 0, so we're going to stay at the high voltage. A 1 transitions, 2 zeros in a row, so we don't transition, 2 1s in a row, transition high, transition low, 3 zeros in a row, no transitions, and finally a 1 transitions to a high at the end. On both of these, if we had assumed the opposite case for the voltage coming in, then the entire signal would be inverted. For AMI, alternate mark inversion, also known as bipolar, a 0 gives a 0 voltage and a 1 gives an alternating plus or minus voltage on successive 1s. This one has the advantage that it has a 0 DC value, so we're not really pumping electrons through this system. So we get a 0 on a 0 and alternating pluses and minus voltages on the 1s. And again, we have to make some assumption about the recent past here, that the most recent non-zero voltage I'm going to assume was negative in this case. And therefore, this first one we get is going to take us positive. The next one then will take us negative. And then a couple zeros in a row. The next one should be a positive, 0. And then the next one will be negative. The next one will be positive. The next one will be negative. Like this. And then a 0. And then the next one will be positive. And then back down to a 0. Okay? And so this one, I'm going to do the same thing. I'm going to assume that the recent non-zero voltage was negative, and therefore I'm going to be going from some value. I guess I could assume what the previous value was. I'm going to assume that the previous value was a 0, and I'm going to go positive on this one then negative, then positive again, and then back down to 0. The next one gives me a negative, couple zeros, next one gets me positive, next one takes me negative, and then 3 zeros in a row, and finally positive. Okay, so this is how the signals look for the AMI. PT, pseudoternary. It's just the opposite of bipolar. It's alternating plus and minus on successive zeros, but a 1 gives a 0 voltage this time. So let's see, a 1 gives a 0 voltage. Let's assume that the last non-zero was negative for the PT, and then we'll go positive on this 0 value. On these two 1s we get a 0 voltage. On this next 0 we go negative, then we go positive, and then on the 1 we go back to 0. The next 0 takes us negative. 3 1s in a row leave me at 0. The next 0 goes positive. The 1 takes me to 0, and the next 0 goes negative. Okay? So you can see this is pretty straightforward. Let's assume that we had a negative value, and so the 1s are going to keep me pegged at 0 for a little bit. The next 0 is going to go positive. The next 1 takes me back down to 0. 2 zeros in a row take me negative, positive. 2 1s keep me at 0. 3 zeros take me first negative, then positive, then negative, and a 1 keeps me at 0. Finally, the Manchester codings. These are the most complicated to argue your way through. Always a transition at the middle of a bit period, and a 1 gives a low to high, and a 0 gives a high to low. Okay, so always a transition at the middle of a bit period. You know what I'm going to do? I'm going to go ahead and draw the zeros first. A 0 goes high to low, and so all of the zeros are going to look like this, high to low, and I'm just going to draw them first. Here's another 0 high to low, and another 0 high to low. Unfortunately, they're overlapping a bit. And the 1s are low to high. Sometimes they match up, sometimes they don't. And we're going to make them match up when we complete the waveform. So low to high, low to high, low to high, low to high. And those places where it hasn't matched up yet, I'm going to go ahead and draw that in. And so this is the easiest way to do these things. Manchester, a 1 is low to high, low to high, 3 1s in a row, low to high, low to high. So these are kind of fun, but they're also a little bit tedious, not very difficult conceptually. And a 0 is a high to low. And I get all these matching back up again. And I won't answer that. Finally, differential Manchester, always a transition at the middle of the bit period. 0 adds a transition at the beginning of the bit interval, and 1 has no added transition at the beginning of the bit interval. So you have to do this one in the order of the bits. 0 is an added transition at the beginning. So let's assume that we start off with a 0 here. Always a transition at the middle. Okay, so let's assume we start off at 0 and we have a transition at the middle. And a 0 means an added transition, and a 1 means no added transition. So we get a 1 bit here, so we have no added transitions. But we still have to transition in the middle of the bit period. A 1 means no added transition. So a 1 comes up and I stay down at 0 and I transition in the middle of the bit period. A 0 means an added transition, so I have to go down and then transition in the middle of the bit period. A 0 adds a transition at the beginning, keep it at the middle. None at the beginning, keep it at the middle. Added at the beginning, keep it at the middle. None at the beginning, keep it at the middle. Another 1, none at the beginning, keep it at the middle. Another 1, none at the beginning, keep it at the middle. A 0, add the transition at the beginning, keep it in the middle. A 1, don't add it, but keep it in the middle. And a 0, add it at the beginning, keep it in the middle. So these are the most complicated to do. So hopefully that way of looking at it helps. Yikes, my video is getting long here. So let me go ahead and assume that I start off like this. And a 1 doesn't add 1 at the beginning, but a 0 does. And a 0 does, and another 0 does again, and a 1 doesn't, but a 0 does, 0 does again, 0 does again, and a 1 doesn't. Okay, so there you go. Hopefully that picture helps. Thanks.